The Pacific Ocean is entering a phase that climate scientists have been monitoring very closely for months, and the latest atmospheric and oceanic data now suggests that the developing El Niño event of 2026 may become one of the dominant global weather drivers heading into the second half of the year. At first glance, the warming taking place across the equatorial Pacific may not seem unusual. Ocean temperatures fluctuate naturally every year. But what has captured the attention of meteorologists is not simply the warming itself, it is the speed structure and geographic expansion of that warming, combined with the increasingly organized atmospheric response developing above it is our. Taken together, these signals indicate that the Pacific may be transitioning into a much more amplified El Niño state than originally expected earlier this spring. To understand why this matters on a global scale, it is important to understand what El Niño actually is from a scientific perspective. Under normal Pacific conditions, strong easterly trade winds push warm surface water westward toward Indonesia and northern Australia. As that warm water moves west, colder and nutrient-rich water rises near the western coastline of South America through a process known as upwelling. This circulation pattern helps maintain one of the most important climate engines on Earth, the Walker circulation. The Walker circulation controls large-scale rising and sinking air across the tropical Pacific. Rising air tends to produce clouds, thunderstorms, and rainfall. Sinking air suppresses cloud formation and often leads to drier conditions. When the Pacific remains in balance, this circulation pattern helps stabilize rainfall distribution across multiple continents. But during El Niño, that balance weakens. Trade winds begin slowing down. Sometimes they weaken dramatically for extended periods. As the winds weaken, warm water that had previously been concentrated in the western Pacific begins migrating eastward toward the central and eastern Pacific Ocean. Once that occurs, the atmosphere begins reorganizing itself around the newly displaced heat source. This is where El Niño transforms from a simple ocean temperature anomaly into a global climate event. Right now, several Niño monitoring regions are already reporting significant positive temperature anomalies. The Eastern Pacific, particularly the Niño 1+2 region near Peru and Ecuador, has shown some of the most aggressive warming signatures. Sea surface temperatures in that area have climbed more than 2 degrees Celsius above long-term averages in some recent observations. That is significant for one major reason: timing. Historically, stronger El Niño events usually take longer to mature. Ocean temperatures often begin intensifying during summer before peaking near late autumn or winter. But in 2026, unusually warm anomalies are already well established before the start of meteorological summer. That early development has raised concern among long-range forecasters because early season oceanic heat often increases the probability that atmospheric feedback mechanisms will have more time to strengthen the event later the year, and the surface warming is only part of the story. Beneath the Pacific Ocean, scientists are also detecting large reservoirs of abnormal heat expanding through the subsurface layers of the equatorial Pacific. In several regions, roughly 100 to 200 meters below the surface temperature anomalies have reached approximately 4 to 6 degrees Celsius above normal. Some localized pockets earlier this year reportedly approached even stronger values. This subsurface heat is critically important because it acts as stored energy for the climate system. Warm water beneath the surface does not remain trapped indefinitely. Over time, oceanic wave dynamics and changes in wind patterns can force that heat upward toward the surface. When that process intensifies, surface temperatures rise even more rapidly, strengthening the atmosphere-ocean coupling associated with El Niño. One of the main mechanisms involved in this process is the development of downwelling oceanic Kelvin waves. Kelvin waves are large-scale pulses of warm water that travel eastward beneath the Pacific Ocean. They are often triggered by weakening trade winds or strong westerly wind bursts. As these waves move eastward, they transport deeper warm water toward the eastern Pacific, reinforcing already existing temperature anomalies. Meteorologists have already identified multiple Kelvin wave signals developing across the Pacific Basin in recent months. At the same time, atmospheric conditions are beginning to align more closely with a mature El Niño pattern. Trade winds across parts of the Pacific have weakened noticeably, while intermittent westerly wind bursts continue appearing across the western and central Pacific. This matters because wind anomalies help reinforce ocean warming. The climate system essentially begins feeding itself. Warmer oceans weaken the trade winds. Weaker trade winds allow even more warm water to move eastward. That additional heat then further alters atmospheric circulation. The cycle can intensify rapidly if the feedback loop remains uninterrupted. Pressure anomalies across the Pacific are also beginning to reflect this transition. Lower than average surface pressure is gradually emerging across the central and eastern Pacific, while relatively higher pressure persists closer to Indonesia and northern Australia. This pressure contrast is one of the classic atmospheric fingerprints associated with El Niño development. Scientists also monitor another critical index, known as the Southern Oscillation Index, or SOI. The SOI measures pressure differences between Tahiti and Darwin, Australia. Sustained negative values often indicate weakening trade winds and strengthening El Niño conditions. Recent observations have shown increasingly negative trends, further supporting the idea that the atmosphere is responding to the warming ocean below. The reason forecasters care so much about these details is because El Niño can alter weather patterns on a planetary scale. Across North America, one of the most immediate impacts often involves changes in the Pacific jet stream. Under stronger El Niño conditions, the subtropical jet stream frequently shifts farther south and becomes more energized. That shift allows Pacific storm systems to track more directly into California, the desert Southwest, the Gulf Coast, and portions of the southeastern United States. As a result, these regions often experience wetter than average winters. California in particular can see significant increases in rainfall and mountain snowfall during strong El Niño years. For reservoirs and drought-stricken regions, this can provide meaningful water relief after prolonged dry periods. But there is another side to that equation. After long droughts, soil conditions often become hardened and less capable of absorbing sudden heavy rainfall efficiently. Burn-scar regions left behind by wildfires become especially vulnerable to flash flooding and debris flows. In mountainous terrain, rapid snowpack accumulation followed by sudden warming events can also increase avalanche and runoff risks. So while El Niño can reduce drought in some regions, it can simultaneously increase flood danger in others. Farther north, across the United States and parts of southern Canada, the pattern often shifts in the opposite direction. Strong El Niño winters tend to favor warmer than average conditions across portions of the northern tier states due to changes in storm track placement and jet stream orientation. However, regional outcomes are never perfectly uniform. Even during historically strong El Niño events, local variability still matters. Blocking patterns in the Arctic, sudden stratospheric warming events, and shorter-term oscillations can temporarily override or distort the broader El Niño signal. That is why meteorologists avoid guaranteeing exact seasonal outcomes months in advance. At American Sky Brief, one of the most important things we continue emphasizing is that climate signals should never be viewed in isolation. El Niño creates a background pattern, but regional weather outcomes still depend on how multiple atmospheric systems interact over time. Globally, the atmospheric consequences become even more complicated. As convection and rising air shift eastward into the central Pacific regions that normally rely on tropical rainfall can begin drying out. Indonesia and Australia are particularly vulnerable during stronger El Niño years because thunderstorm activity often weakens across those areas. Reduced rainfall can increase agricultural stress, strain water supplies, and dramatically elevate wildfire risk. Historically, some of the world's most severe wildfire seasons in Indonesia and Australia have coincided with strong El Niño conditions. Drier vegetation, prolonged heat, and reduced humidity create highly combustible environments capable of supporting large-scale fire outbreaks. Monsoon systems can also weaken. Parts of India, Southeast Asia, and even portions of Africa sometimes experience disrupted rainfall patterns during major El Niño events. These rainfall shifts can affect food production, hydroelectric generation, and freshwater availability for millions of people. And then there is tropical cyclone activity. One of the most misunderstood aspects of El Niño is its influence on hurricanes and typhoons across different ocean basins. In the Atlantic Ocean, El Niño typically increases upper-level wind shear. Wind shear refers to changes in wind speed or direction with height in the atmosphere. Strong shear disrupts the vertical structure hurricanes need in order to organize and intensify. As a result, Atlantic hurricane seasons during El Niño years are often less active overall. But the Pacific frequently responds differently. Warmer waters and more favorable atmospheric conditions can support increased tropical cyclone development across the eastern and central Pacific basins. Typhoon activity in portions of the western Pacific can also become enhanced depending on how atmospheric circulation evolves later in the season. In other words, El Niño does not eliminate storm energy from the planet. It redistributes it. Long-range climate models are now attempting to estimate how intense this event could become by late 2026. Some ensemble forecasts already suggest a strong El Niño is possible by autumn and winter. A smaller number of aggressive model runs hint at anomalies approaching levels observed during some historically powerful El Niño event. Still, forecasters remain cautious. Climate models contain uncertainty, especially several months into the future. Ocean-atmosphere interactions are highly complex, and small changes in wind behavior or ocean heat transport can significantly alter long-range projections. A system that appears extremely strong in May can weaken unexpectedly later in summer. The reverse can also happen. Several historic El Niño events intensified rapidly only months before reaching peak strength. That is why most scientists avoid using terms like historic too early. At this stage, the most scientifically responsible conclusion is that the probability of a moderate to strong El Niño is increasing steadily, while the possibility of a very strong event cannot yet be ruled out. Even a moderate event would still carry enormous implications globally. Agriculture, fisheries, shipping, logistics, energy demand, insurance markets, water resource management, and disaster preparedness systems are all influenced by large-scale climate oscillations like El Niño. Entire economies can feel the impact of changing rainfall patterns and shifting seasonal temperatures. That is why scientists continue monitoring every atmospheric wave, every wind anomaly, every pressure trend, and every new ocean temperature update so carefully. Because the Pacific is no longer behaving like a neutral system. The atmosphere is beginning to reorganize itself around a warming ocean basin. And if the current trends continue through summer and into early autumn, the second half of 2026 could be heavily shaped by one of the most powerful climate mechanisms on Earth, El Niño. For continued long-form climate analysis and data-focused weather breakdowns, follow American Sky Brief as we continue tracking the evolution of this developing Pacific pattern in the months ahead.